Okay, in last class we were discussing how interference pattern is observed when waves the wave passes the same wave passes from two slits, and then diffracted waves they interfere with one another. We observe constructive and destructive interferences, and this is what we observe. And the fringe separation depends on wavelength and distance and slit separation. Now, that is the ideal case. This is the ideal case. If all of the waves, if both sources are in phase and both of the slits are of same opening, that this is what we should observe. But what if we start changing things? Number one, if we make two sources have a phase difference of 180 degree. If both of the sources have a phase difference of 180 degree, the point where we should observe a destructive interference, we get a constructive interference. And the point where we should get a constructive interference, we should get a destructive interference. See, I hope you can see the red lines over here. They are pointing on constructive interferences and destructive interferences. The point where you see zero wavelength, the red lines, they should be destructive interferences. And the blue lines, they point to constructive interference. So where the power difference will become identical, one wave will get a crust over there, the other wave will be bringing a trough. So crust and trough or waves which are 180 degree out of phase, they will produce a destructive interference. Similarly, if we make one of the slit wider, what will happen then? In that case, fringe separation will stay same. The only difference will be the point where there will be a constructive interference. There will be a bigger constructive interference because one slit will be allowing more wave to come, more energy to come through. It means more amplitude is coming from one source and less amplitude is coming from the other source. So the bright regions will become more bright and dull regions or dark regions, they will become brighter as well. Now, we can practice these wave questions later. Let's first complete the syllabus. There's a thing coming your way, which is known as diffraction grating. Instead of having any limited number of two or three number of fringes, what if we have 1,000 fringes in a millimeter? What will happen then? What kind of interference pattern we will observe? See, this is diffraction grating, and then when wave passes through this one, this is a diffraction grating. So when wave passes through this one, we have regions of maximum interference. We call them maximal. So the one in the original line of the wave is called zeroth maximum. The one that is on the side of the zeroth maximum, they are called first maxima, and then second maxima, and then third maxima. And this pattern is symmetric on both sides of the zeroth maximum. The angle that any maximum makes from the point where the wave is hitting the diffraction grating is theta. So this is a very common formula for diffraction grating. D sine theta equals to n lambda, where D is the line separation. So if there are so many lines, this gap between the two lines will be D. Okay, D is the gap between the two consecutive lines. D theta is the angle between the zeroth order and the order we are studying. N is the number of the order, and lambda is the wavelength. So for maximum number of orders, because you can see that orders are making angles, so the last order will be making 90 degree angle. So when we assume that theta is 90 degree, and in that case, the order will be the maximum order, we put everything into the formula and we get this formula for maximum number of orders, which is D divided by M. And remember, this will give you number of orders on one side of the zeroth order. So in order to get the total number of orders produced, we will double this number and then add one to it. Okay. Diffraction grating, and after this we should discuss stationary waves. Now see, stationary wave is a phenomenon when two identical waves superpose from two opposite directions. If two waves of same nature are coming from exact opposite direction, and they superpose from two opposite directions, they will produce a pattern which is known as stationary wave. In this case, what is happening is energy is not moving anywhere. If one wave is trying to make energy go towards right at the exact same rate as another wave is transferring energy to the left, then energy will not be going anywhere with respect to its position. Energy will be stationary. So stationary waves mean energy is not going anywhere. So this stationary wave, it produces nodes and antinodes. What are nodes and what are antinodes? When stationary waves are established in a string or a surface of water or any field, for example, sound wave can produce um, stationary waves in 3D in space. So the points where there will be a destructive interference and there will be no energy to a particle will be having least amplitude or no amplitude at all. That point would be called node. Node means a point with no energy, and antinode means a point with maximum energy. And there will be points in between as well. Some points have maximum energy that are at the position of antinode, and the points that have no energy at all that are at the position of nodes. So nodes and antinodes, this is a more detailed diagram of nodes and antinodes. Uh, Between two consecutive nodes, and this is for the stationary waves only. In progressive wave, all of the particles in one wave, they are out of phase with one another. But in the stationary waves, all particles between two consecutive nodes, they're always in phase. Okay? So if one particle is going up, all of the particles will be going up. If one particle is coming down, all of the particles will be coming down. So between any two nodes, all particles are in phase. Net energy at a point does not change. All particles between two consecutive nodes are in phase. All particles on one side of node are 180 degree out of phase from any particle on the other side of the node. So one side of the node, if one side of the node particles are going up, on the other side of the node, particles will be coming down. So let's focus on this thing. Let's say this is particle X. This is particle X, and this is particle Y. If X particle is going up, Y particle must be coming down. And if Y particle is coming down, then all the particles on that side are coming down because they're all in phase. So all these particles will be coming down. So if you observe any node, particles on one side are exactly opposite to the particle on the other side. That means 180 degree out of phase. Now, in stationary wave nodes and antinodes are formed. One good use of everyday use is microwave oven. In microwave ovens, microwaves are produced from one side and there is a reflector on the other side. So microwaves hit the reflector, come back, and they form stationary waves in between. Okay, the distance between the plates and a reflector and wavelength of the microwave is controlled. So it always produces uh, stationary wave in between. And if you put something over there, the natural frequency of the water molecule matches the frequency of microwaves used over here. So water particles which are at the position of nodes, antinodes actually, they will have greater amplitude and their kinetic energy increases, and this is how something becomes hotter. The molecules gain kinetic energy, and whatever you put over there, whatever food you put over there, becomes warmer or hotter. So one important thing that anything that you put in a microwave should have some water content in it. If it does not has any water content, there's no way you can heat it up, because microwaves can only heat water. So this is an example. This is a stretch string. So in stretch string, we can see waves, stationary waves produced. One example is guitar string. For example, at t equal to 0, it is a straight line. After quarter of a time period, you should see a wave like this, like position of the particle is this, like this. And then at half of the time period, the string becomes straight again. At 3/4, the particles are in opposite position, and when one time period completes, particle come back to the original position. But what happens is we see these situations one after the other. This is actually these lines are taken from the diagram above. For example, look, this is the same wave. Similarly, this is the same wave. So stationary wave, we show stationary wave like this, but actually it is multiple happenings on the top of one another. That's why we observe wave as seen in the first diagram. But actually the particles are moving up and down and they produce this image. And there comes times when the string is perfectly straight within an oscillation. Now, so if you have a tied rope like this and you want to establish stationary waves, you need to have a node on the part that is tied. For example, this wave, you can see it is tied on both ends. So it should have a node on both ends. It will have nodes on both ends. The end that is tied will have node. The end which is loose, which is open, which can move, that end should have an antinode. Now, see the first one. We have a rope which has a length L. It is tied on both ends. It is tied on both ends. So if wave is tied on both ends, then when stationary wave is established, it should have node on both ends. Tied and must has a node. So this is the longest possible wavelength that can establish a stationary wave. There will be node on one end and node on other end. Remember, from one node to another node, distance is exactly half of a lambda, because you are only looking across of a wave. Like if you consider the top position, you're only looking at a crust, there will be a trough afterwards. or if you're looking at the bottom possible position, if that is stuck, there will be a crust coming on its way. So you're looking at two different waves, crust of one and trough of the other. So from node to node, it is half of a lambda. So in this case, length will be half lambda, or lambda will be equals to 2L. And the frequency is the lowest possible frequency which can establish a stationary wave. So if we start increasing the frequency and decreasing the wavelength, the stationary wave phenomena will disappear, because for any different length, it will not be producing node on both ends. But if we keep on increasing the frequency gradually and decreasing the wavelength, we can come to a point where we can have another stationary wave like this. This one has a smaller wavelength and higher frequency. In this case, you can see we have one complete wave going in one direction, one other wave going in the other direction. So we have one complete wave between the two node points. So in this case, length equals to wavelength, and the frequency of this wave, because in this case we have reduced the lambda to half, the frequency must be 2f naught. This case, frequency will be twice the fundamental frequency. If we increase the frequency again and decrease the wavelength, the phenomena of stationary wave will disappear. But if we keep increasing frequency and decreasing wavelength, there will be a time when we will have another stationary wave established between the two points. In this case, we have 3 nodes and so actually 4 nodes and 3 antinodes. In this case, length L will be equal to 3/2 wavelengths. And in this case, the frequency of this wave will be 3 times more than the pulse frequency. And similarly, we can establish any stationary wave which is multiple of this thing. So, now the second possibility is if we have wave tied end on one end. On one end, the wave is tied. On the other one, it is open. It can move up and down. So in this case, we must have a node on the tied end and antinode on the open end. So this is the first possible wave that we can produce. Remember, this will be the length L. What do you think? What will be length L equals to? How many wavelengths? Length L will be equal to how many wavelengths? It is starting from node and ending at an antinode. This frequency will be equal to the fundamental frequency or the basic frequency which can establish a stationary wave. Remember, if node to node is half of a wavelength, then node to the antinode, the nearest antinode, it should be quarter of a lambda. So that means lambda equals to 4L. So the next possible wave will be if we increase the frequency and decrease the wavelength, the next possible wavelength will be like this. Now, this is a node, node, antinode, and antinode. In this case, L will be equal to how many wavelengths? 3/4 of a wavelength. And frequency will be, it is a node, antinode, antinode, node, node, antinode. So you can see it is 3 times more of a wave than in the first one. So this means that the frequency will be 3 times of the fundamental frequency. This frequency will be 3 times of the frequency in the previous case. And lambda will be 4/3 times of L. Okay. So this is for you. If this is the case, what will be lambda equals to? What will be the frequency equals to? Hurry up. So as you can see from node to node, it is 0.45 of a lambda. And then from node to other node, it is also half of a lambda. From node to antinode, it is quarter of a lambda. So L should be equal to 5/4 of lambda, which will make lambda equals to 4/5L. Remember when the frequency was F naught, lambda was 1/4. Sorry, lambda was 4L. So now it is 4/5L. So it means you have reduced length by wavelength by 5 times. If you reduce wavelength by 5 times, you will definitely increase the frequency by 5 times as well. So this frequency will be 5 times of fundamental frequency. Similarly, in this case, you have a node, 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 a node. That will make 1.5 of lambda. And then we have a quarter of a wavelength. So it will make 1.75, which is 7/4 lambda. So length equals to 7/4 lambda. Lambda equals to 4/7. So that means I'm now making wavelength reduced by 7 times, and this will increase frequency by 7 times. Okay. So this is for the waves which are tied on one end and loose on the other. What if a string is loose on both ends? It's just a string, and there are sources on both ends that are making it oscillate up and down. And they can establish stationary waves in this one. To establish stationary waves in this one, we have to have antinodes on both ends. It is an antinode here, node in the middle, antinode on this end. So In this case, if we start from antinode, end on antinode, what do you think? What will be distance L equals to in terms of lambda? Remember, if distance from node to node is half lambda, then it is half lambda if we go from one antinode to another antinode. And this frequency, because this is the basic wavelength and the largest wavelength and very small frequency, the least frequency that can establish a stationary wave. So we will call it F naught. The frequency will be naught. The next possibility is we have an antinode here, an antinode here, antinode in the middle, and two nodes. In this case, the length L will be equal to wavelength because we have increased the wavelength 2 times. The new frequency will be 2 times of F naught. Antinode, antinode. This is one wavelength. This is another wavelength. So in this case, L equals to 2 lambda. Lambda equals to 1 over 2L. This will make frequency to go 4 times. L lambda, lambda. So this is L equals to 4 lambda. Lambda equals to 1 over 4 L. So frequency will be equal to 8 times of fundamental frequency. Okay. So this is about the stationary waves that are established in string. Stationary sound waves. In the diagram, we make them very much like the transverse wave, but we all know that sound waves are longitudinal waves. When longitudinal waves are shown on diagram, for the simplicity, we draw them like transverse waves. So we have nodes here, 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 here. But actually, these are longitudinal waves. This is what you can see. I hope on your screen you can see them. The particles are vibrating forward and backward. And this is how the stationary waves behave. This is where the antinode is. You can see these particles are oscillating with greater amplitude. This is where the node is. This is also where the node is. But I don't think this kind of diagram is easy to draw again and again. Because this will take time. So for the simplicity, what we do is we draw the diagram of a transverse wave to show longitudinal wave. This would mean like this is node, this is node. So these particles are not oscillating at all. These particles are oscillating with slightly greater amplitude. These particles so this is what is happening. Some of the particles are oscillating with smaller amplitude. Then next particles are oscillating with more amplitude. The particles at antinode are vibrating with maximum amplitude and so on. Gradually, there will be particles which are not vibrating at all. So those particles are called nodes. But this diagram is again, even if you draw one line, it will take time because you have to show oscillations of different particles separately. In sound waves, this is how it actually happens, but this is how we show it for the simplicity. So we will not be making the diagram for the longitudinal wave. We will be taking help from the transverse wave to show longitudinal waves. To establish stationary waves in pipe, sound stationary waves in pipe, there can be multiple options. For example, we can have open pipe from both ends. We can have pipe which is closed on one end, and there can be a possibility of pipe closed on both ends. But no, if we have pipe which is open on both ends, the rule for establishing station waves in pipe is that there must be an antinode on open end, there must be a node on the closed end. Single frequency sound is used. If you are making station wave, as in case of open from both ends, you have to use two sources. They both should have same frequency and same wavelength. And when wave goes like this, to establish a station wave in a pipe which is open on both ends, this is the largest wavelength and smallest frequency. Okay, so well, if your mind can compare it with the previous example, it is okay. This is it is good. The open end is like loose end for the string, and closed end is very much like tied end for the string. So this is open on both ends, so it is loose on both ends. So we have antinode on both ends. Length of the pipe is half of a lambda. Lambda will be 12, and this is the fundamental frequency f naught. Now, next possibility is this. So if this is the next possibility, what will be wavelength and what will be frequency in this case? So we have antinode, antinode, antinode. So from antinode to antinode, half lambda, then again antinode to antinode, half lambda. So L should be equal to 1 complete lambda. So L is lambda, or lambda equals to L. And because we have increased the length 2 times, the new frequency will be half of the, new frequency will be double of the fundamental frequency, 2M. Similarly, if this is the case, how many wavelengths do you think have fit into the pipe now? So we have an antinode, 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 one wavelength, antinode, 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 another wavelength. So in this case, we can see there are 2 complete wavelengths over there. So L will be equal to 2 lambda, lambda will be equals to half of L. The new frequency will be 4 times of the fundamental frequency. And this is how we can make any diagram and find out how many wavelengths are there. A more common thing that we use to establish station wave is like with one source and a pipe which is closed on one end. So if you use a pipe which is closed on one end, this will be producing a node on the closed end and antinode on the open end. For the smallest frequency, this should be the case. This will be the smallest frequency and largest wavelength, node and antinode. L in this case equals to the distance between node to antinode. Now, node to antinode in terms of lambda, how many lambdas are there from node to antinode? quarter.
Yes.
So length will be equal to quarter of lambda. Lambda will be equal to 4L, and this frequency will be taken as fundamental frequency for this example. If we increase the frequency or decrease the wavelength, this phenomenon of stationary wave will disappear because there will be not an antinode on the open end. But if we gradually keep increasing frequency and keep decreasing wavelength, there comes a time with the passage. After some time, we can have this situation. Again, there is an antinode on the open end and node on the closed end. So in this case, the same length of the pipe is equal to how many wavelengths? So node to node is half of lambda, node to antinode is quarter of the lambda. So the length L is equal to 3/4 of wavelength, 3/4 of lambda. That will make lambda equals to 4/3, and frequency will be equal to 3 times of fundamental frequency. Next possibility is this, and then there are multiple possibilities, and we can find out the length and the frequencies. What are the uses of establishing stationary sound waves in pipe? One is that we can use this apparatus to find out wavelength of sound, which is not an easy thing to measure, wavelength of sound. But if we use stationary wave phenomena, we can measure wavelength of sound. Let's see how. If this is a pipe, this example, this is pipe, this is water, and we can make the pipe move up or down. When we make the pipe go up and down, we can change the air column in the pipe. The water surface inside the pipe will be acting as a reflector. So one possibility is that we can, and this is a source of sound with unknown frequency and wavelength. So what we do is we remove all of the air from the pipe. So we almost fill it with the water, and then we gradually make the pipe come out, and we wait for the first stationary wave to establish. And when we see the first stationary wave over here, what is the symbol? How do we know that there is a stationary wave established in the pipe? Answer is we hear a loud sound, because you can see this is an antinode. So we hear a loud sound. So we can hear a loud sound when there is an antinode or established on the open end. Similarly, again, because it is an antinode, so we will be hearing a loud sound. So when we hear a loud sound, it means and there is an antinode. So what we can do is when we hear the first loud sound, we can mark on the pipe where the position of the water is, and then we can mark on the pipe again when we have another antinode on the open end. We can use that. If we can measure this distance, that will be half of a lambda. And this is how we can measure the wavelength of sound wave from an unknown source. Now, it doesn't matter whether you do it with the first and second antinode. For example, if it is one to third antinode and it is fourth antinode, the difference between the height of these two will still be half of lambda. So if we hear a loud sound and we start lowering the water level and we hear another loud sound, the difference between the two levels of water inside the pipe will be equal to half of lambda. So we will be using different technique. Let's solve a question. Here's an example. Define the wavelength of a progressive wave. Distance, that energy moves in one time period is called energy. That this energy moves in one time period is called wavelength. Distance between two consecutive in-phase particles is also called wavelength. Or distance between two consecutive in-phase particles equals to wavelength. Now, state what is meant by antinode of a stationary wave. It is a position of maximum amplitude. It is a position of maximum amplitude. Now, a loudspeaker is producing sound of a constant frequency. So one single frequency sound is produced by the loudspeaker in a pipe. Okay, we were changing air column using water level. Can we change it using a piston, as in this diagram, like by making the piston move outward or moving it towards the loudspeaker? We can change the air column in the pipe, and that can also help us to establish stationary wave. So it is the same thing. Instead of doing it with water, we are using a piston to do that. The movable piston at distance x from the open end of the pipe, distance x is increased from x equals to 0 by moving the pipe between left with a constant speed of 0.75 centimeters per second. The speed of sound is 340 meters per second. A loud sound is first heard at x equals to 4.5 centimeters. Assuming that there is an antinode of stationary wave at the open end, determine the frequency of the pipe. So it is a 3-mark question. And if he says that the first loud sound is heard at 4.5 centimeter, he actually means if this is a pipe, this is a piston, then this is what is happening. There is an antinode over here and node here, and this distance is 4.5 centimeter. Can you use this distance to find lambda? (18 centimeter) or 0.18 meter. So that is lambda. Save it. We need it. V equals to 340 meter per second. Can we use this information to find F? Is there any relationship between VF and lambda? Hello? Is there any equation, any formula that connects V, F, and lambda?
Yes.
Oh, actually, the point. This means I need that formula.
Sir,
You said sir, and then
lambda is equal to VT.
no, V equals to F lambda.
Oh, sorry.
V over lambda. So 340 divided by 0.18. Use a calculator. So it will be 1900 hertz. Let me check using calculator. 340 divided by 0.18. Yes. So 1900 hertz. After time interval of a second, much louder sound is heard. Calculate the time interval. Another loud sound will be heard after half of lambda. Distance must be 1/2 lambda, which is 1/2 into 18, 9.0 centimeter. Speed equals to 0.75 centimeter per second. 0.75 meter per second. So time will be equal to distance divided by speed. (12 seconds). So these kind of questions, they appear in exam. Tomorrow we will be doing electromagnetic waves, and then this chapter will be done. And then we can do some past paper questions. Okay. So you prepare.